Lesson 4.8, Analyzing Graphs of Polynomial Functions. If we have a polynomial function, then we know these four things. If k is a 0 or root, so k is a 0, then k is a solution for f of x equals 0. It's actually the definition of 0. It's why we call it a 0, because it makes the function equal 0. We also know it's an x-intercept if it's a real number, and that x minus k is a factor of the polynomial. We can graph a polynomial function a little bit easier if we know all the x-intercepts. Consider this function f of x equals 1/2 x plus 2 squared, x minus 3. Since x plus 2 and x minus 3 are the factors, the x-intercepts are -2 from there and 3 from there. So what we'll do is we'll graph the x-intercepts and create a table of values to finish plotting the points around the x-intercepts. And then we draw a smooth curve through the points. So let's try graphing this function. So we already said that we know the x-intercepts are -2 and 3. So -2 and 3. So we're going to make a table of values, and it should be around the x-intercepts. So I use my calculator, and I get -4, -14, -3, and -3, -2 and 0, -1 and -2, 0 and -6, 1 and -9, 2 and -8, 3 and 0, and 4 and 18. And everything else is way off the graph. Even these are kind of high, so I think in the y I'm going to have to count by 2's. Alright, so my first point, -4, -14 still doesn't fit. -3, -3. So I'm going by 1's in the x. Guess I should put those on. -2, 0, I already have. -1, -2, 0, -6, 1, -9, 2, -8, 0, 3, and then 4, 18 is way up here somewhere. Alright, so we didn't make it to -4, so our graph line is going to come up. It's going to touch. I know it doesn't cross there because it's multiplicity 2. When it's multiplicity 2, it doesn't actually cross the x-axis. So the other one is multiplicity 1. It does cross, and I'm heading up way high. Something like that. And there's our graph. Notice it's smooth curves, smooth corners. There's no sharp corners or anything. Just all nice and smooth. Since the graphs are all smooth with no holes or sharp corners, we have something called the location principle. It says if we have a polynomial function and a and b are two real numbers, such that f of a is less than 0 and f of b is greater than 0, then f has at least one real 0 between a and b. So in other words, if we have our graph, and let's say here is a and here is b, so I know some point is negative in the A positive at B, notice in between there must be a 0. So that means we can use the table feature in the calculator and find locations to look for where the y values change signs. So the zeros are always between the corresponding x values. So if x and y in a table, and here at 2, y is -3, at 3, y is 4, I know somewhere in between there must be a 0, because between -3 and 4 is a 0, so a 0 must be between x equals 2 and x equals 3, because the y values go from negative to positive or positive to negative. So let's find all the real zeros of this. Don't think factoring will work, so let's do p's and q's. P's are factors of that, of the constant, so that's 1 times 18, 2 times 9, 3 times 6, that's what 2 times 9, and 1 times 18. Q's are factors of the leading coefficient, so that's 1 times 4 or 2 times 2. So p's over q's, wow, there's a lot of them. Let's go 1 over 1, 1 over 2, 1 over 4. 2 over 1, 2 over 2 I already have. It's the half. 2 over 4 I already have. It's a quarter. Oh, sorry, it's a half. 3 over 1, 3 over 2, 3 over 4. 6 over 1, 6 over 2 is the same thing as 3, which I have, and 6 over 4 is the same as 3 halves, which you already have. 9 over 1, 9 over 2, 9 over 4, 18 over 1, 18 over 2 is 9, I already have that. 18 over 4 is 9 halves, which I already have. So that's our list of p's and q's. So I'm going to look at a graph or make a table. So I made a table. All right, so I can see right there is a change in sign. So that is between -2 and -1. So I need a value between -1 and -2. And so I think we might try -3 halves. Because that'd be, between that, because -3 halves is -1.5. So if I put -3 halves and do synthetic division, bring down the 4 and multiply, and I think you get -6. Add and multiply, I think you'll get -33. Add, multiply, there we go. So a mistake. Sorry, it's not 8, it's a 12. It's -12. And that gives us 18, and we get a 0. That was x cubed. So now our depressed polynomial is x squared. We could try factoring that. So we factor out a 2 maybe. And can we factor that further? To get a 2x squared, it'd be 2x times x. And to get a negative 6, maybe a negative 1 and a plus 6. I don't know, see if that works. It'd be 12x minus x is 11x. Hey, that's what I wanted. So that worked. Okay, that still equals 0, so I can take each factor equal to 0. Here I get x is a half. Oh, hey, look at that. We had a sign change there between 0 and 1. Notice a half is between 0 and 1. And what's not on my table is another 0 was at negative 6. So all our zeros are negative 6, negative 3 halves, and 1 half. Again, notice that one is right there between negative 1 and negative 2. That one's right there between 0 and 1. Graphs also have what are called turning points, which are local maximums or minimums. It's where they turn from going up to going down or from going down to going up. So it's that point or that point. The graph of every polynomial function of degree n can have at most n minus 1 turning points. So if your degree is 4, you can have up to 3 turning points. If all the zeros are real and different from each other, then you'd have exactly n minus 1 turning points. Calculus lets you find turning points easily. For us, we're just going to look at a graph. So what are the turning points in this graph? Well, we look for the highest areas in the, like right there. So that's the highest in the area. So that appears to be a maximum at negative 1, 0. And then down here appears to be a minimum, because it's the lowest in the area at 1, negative 4. So I have a total of 2 turning points. So since there's 2 turning points, and that's n minus 1, our degree could be 3.